Lab 8. Amanda Acosta, Alyssa Rodriguez, Alyssa Olguin, Montserrat Nunez.
Faraday's law of induction describes how a changing magnetic field produces a voltage in a coil. The amount of voltage generated depends on how quickly the magnetic field changes. This principle is important for understanding how electricity is produced in many real-world systems. For example, in our lab, a magnet was dropped through a coil connected to a voltage sensor to measure the induced EMF. Magnets with different magnetic field strengths were used while keeping the motion of the magnet as consistent as possible. The magnetic field of each magnet was measured and the corresponding voltage produced in the coil was recorded and compared. The purpose of this lab and experiment is to determine how changes in magnetic field strength affect the induced voltage and to test whether they are directly proportional. It is predicted that increasing the magnetic field by 20% will result in about a 20% increase in the induced voltage.
Induction coil. The induction coil measured the voltage when the magnet was passing through. The coil produced an EMF, bar magnets. The bar magnets dropped in the coil to create a changing magnetic field. Different magnets of various strengths were used. Voltage sensor. The voltage sensor was connected to a coil to measure the voltage produced when the magnet passed through. The magnetic field sensor was used to measure the magnetic field strength of each magnet so comparisons could be made between the trials. The lap stand. This was used to hold the coil in place so that the magnet could fall straight through the center each time. Capstone software. This was used to record the voltage versus time graphs and display the magnetic field readings during the experiment.
We first began by setting up the stand with a clamp, cushion box, and multiple coils, then secured one coil in the clamp so the magnet can fall through its center and placed the cushion box underneath to catch it. We connected the voltage sensor to both ends of the coil and opened capstone, setting up a voltage versus time graph with a sample rate of 100 Hz. Then added a second page with digits to measure the magnetic field using a magnetic field sensor. For part 1, we selected one magnet as the baseline and measured its magnetic field, then measured the magnetic field of the other magnets and calculated the percent increase or decrease compared to the baseline. After that, we dropped each magnet through the coil 5 times, making sure to keep the same orientation and direction for every trial, and recorded the induced voltage in capstone. For part 2, we investigated how the increase of the induced voltage by 20% without changing the magnetic field strength, so we selected speed as our variable. We then increased the speed of the magnet as it passed through the coil by throwing it down faster, again keeping the same side and direction for every trial, and recorded how the increased speed affected the induced EMF. Finally, we saved all the data for analysis.
Table 1, set up values for the magnetic field. This table identifies the sample, shape, and magnetic field for each respective magnet. Our group chose a cylindrical shaped magnet as our base and found that it had a 0.0248 magnetic field with 0% difference. Our sample 1 was the circular magnet and had a magnetic field of 0.0142 with a percent difference of 42%. Sample 2 was a rectangular magnet which had a magnetic field of 0.0121 and a percent difference of 51%. Table 2, results of the EMF induced in the coil for each magnet. This table identifies each sample, their maximum average EMF, and their percent difference. The base sample had a maximum average EMF of 0.27 and a percent difference of 0%. Sample 1 had a maximum average EMF of 0.022 and a percent difference of 91.85%. Sample 2 had a maximum average EMF of 0.11 and a percent difference of 59.26%. Base graph of EMF induced in the coil. Sample 1 graph of EMF induced in the coil. Sample 2 graph of EMF induced in the coil. Step 3. To increase the voltage by 20%, our group decided to change the velocity/time portion of the equation. Using the same setup as our previous experiment, our group chose the cylindrical magnet for this step. The data for this step was achieved by comparing the data to the values found in Table 1 and 2. To reach our goal, our group attempted to push the magnet through the paper funnel at a faster rate than our previous attempt. We found that we had to push the magnet through at a faster rate, but not too fast because then the values would increase by a value greater than 20%. After multiple trials, we were eventually able to meet our goal. We decided to alter time/velocity because it was the only variable that could be changed within the scope of our lab. When testing our procedure, we learned that the electromagnetic force and velocity/magnetic field have an inverse relationship with one another. Therefore, to increase one, you must decrease the other, and vice versa. Overall, doing this step helped us further understand the relationship between these values and how they correlate with one another. When doing this step, we were able to increase our voltage by 17%. Step 3, graph. Conclusion. After completing this lab, our group was able to observe the EMF differences between various shaped magnets, as well as their percent differences. EMF differences were found by averaging the EMF of 5 separate trials for each respective magnet. Because our group chose to use a cylindrical magnet as our base, each additional magnet's percent difference was compared to the cylindrical magnet. These values are shown in Table 1 and 2. After documenting the percent differences in Table 1 and 2, our group observed that the differences were greater when recording EMF. We also observed that the percent difference was higher for Sample 2 in Table 1, magnetic field, but Sample 1 percent difference was higher in Table 2, EMF. Compared to the base, both magnetic field and EMF decreased, thus all changes occurred in the same direction. Because our values were greater than 5%, the differences are not negligible. The ratio of our magnetic field percent difference to EMF percent difference was 0.46 for sample 1 and 0.86 for sample 2. Our results partially support our hypothesis that induced EMF depends on magnetic field strength. It also is important to note that any other potential errors in our experiment were probably due to sensor/equipment error, since we did have some difficulties with our sensor when setting up the equipment. Credits: Introduction, Amanda Acosta. Materials, Montserrat Nunez. Procedure, Alyssa Olguin. Data, Alyssa Rodriguez. Conclusion, Alyssa Rodriguez. Credits, Alyssa Rodriguez. Thank you.